So we have limited time, and I have just been delegated responsibility. Good afternoon, everyone. How are we? I need chalk, but I'm in class. Wait for me after class. Where is chalk? Now, there must be, who is bringing chalk? There must be a difference between science class and any other class. As a matter of fact, regardless of whether all subjects are in here or not, there must be that difference. One of the things that make a science class different from others is the fact that in all my time as a student at A level, I did not, it's on record, I had never entered the class after the teacher had entered. But here it is the order of the day. I did not. I never entered class after the teacher had entered. It had never happened because I had the timetable. I was a class representative. So that one you must check on it. You must check on it. I have made a ground rule in Senior 5 Science 2. I am making the same rule here. Once you come and peep and you realize that I'm in class, go to another class. I have made that ground rule there. I am making it here. If you come and I'm in class, don't even bother to knock. Go to another class, because you will have qualified not to be ready. Now, when we come in again, it takes something like half an hour for people to settle. Really, how do we define that? Thank you. How do we define that? You see, well, we can believe in change as a factor of life. For us, by the time we were young, it was the student, or they were the students to wait for the teacher. Today, it is the teacher to wait for the students. And it is through those movements that people keep on placing the camera. There is nobody who seems to be serious, but then comes in late for class. So, ladies and gentlemen, today I have been delegated to come because the colleague is having unavoidable circumstances. On Wednesday, I'm supposed to meet you from 9:20 to 10:40, right? If you find me in class, don't even bother to knock. Are we together? You simply go and attend another class from somewhere else. That is one, ground rule one. Ground rule number 2 that I've made in 5 Science 2, every scientist who does physical science, that is physics, maths, chemistry, you must have a scientific, non-programmable, silent calculator. Those are the 2 properties that define a scientist, especially a physical scientist. Otherwise, If we don't wake up, we might end up the whole year repeating the same things. Then another thing, it is purely bad manners for right-thinking people in society like this to communicate through the windows in the presence of the teacher. Purely bad manners. That one I cannot say it is for scientists or not, but in a civilized society, can you talk to somebody through the window when your father is seated in the sitting room? Eh? Tell me, Ivan, do you talk to somebody through the window when dad is in the sitting room? Absolutely not. So at school, we are your fathers. So some things need to be, twisted. Energy stored. I think we had looked at the network or capacitor networks, right? Hadn't we? Yes. Capacitor networks. No. We had not. Okay, capacitor network. Let us start with energy stored in a capacitor. Then we go to capacitor networks. Energy stored in a capacitor. Energy stored in a capacitor. Now, we can try to remind ourselves of some principles that we are going to popularly use here. One, how did you people define physics in senior one? Yeah. I know some few names, human, beginning with you. How did you define physics in S1? Yes? The study of matter and how it is related to the energy. Now, generally, it is a branch of science because whoever introduced physics to you started by defining science as the study of, please talk to me. The study of living things. Don't tell me that you don't remember primary science. Whoever introduced science to you told you that science is the study of living and non-living what? Then he said that the study of living things is called biological. She doesn't remember. The study of living things was called what? Biological science. Those people dealing in biology, ecology, all the science that deals with living things is embedded into a branch called biological science. Then the other branch that deals with the study of non-living things is what we call the physical science. Now, under the physical is chemistry, physics. For your information, actually, maths is also an independent language. Isn't it? Isn't it? Because it coexists in actually all the subjects, doesn't it? It coexists in all the subjects. So mathematics is a language. So the chemistry and physics are the branches of science that deal with the study of non-living what? Things. Now, particularly, physics is that branch that looks at matter and how it is related to energy. I'm interested in the concept energy. How did you define energy in S1? Pardon? The ability, but your moral is too low. When I condemn you, you get annoyed, and you go into what we call orusirika. You know orusirika? How do you call it in English? No, it is me to tell you about what you are doing wrong and you rectify. If me I don't, how do you feel when I go and tell a history teacher about the behavior of a physics class. Is it right? I'm supposed to come and tell you that you guys, the way you are behaving is actually you are very fit for history. But when I tell you about it, then again you put on a gloomy face. Then who do you want to tell you about your your behavior? So you've said matter is the ability to do work. Now what is work? Huh? Now, of course, if you got the answer, you put up the hand and we have an organized environment. What is work? Work is a product. You people, remember these things. I don't think you dumped away your physics books, did you? Go and check on them. You need them. Yeah. You need them. Go and keep revising. Work is a product of force times what? Distance, which means that anything that moves from one point to another, it has done work, right? And the moment it does work, its ability to do work is what we define as the energy. So even in charges, if a charge can leave one point to another, then it has done work, right? And when it does work, then we can look at the energy it stores. Because if a force is applied onto anything and it makes that thing move from one point to another, point one, work has been done, right? And if work has been done, energy has been in existence. Are we together? And if energy has been in existence, it means that the force or the energy that made this object move from one point to another is not going to be wasted. Then that one also drives me to you people to remind me of, excuse me, the principle of conservation of energy. How does it state? Or who remembers the statement of the principle of conservation of energy? Yeah. Please. I'm seeing a hand somewhere. At least you appreciate this African here. Appreciate the African. 1, 2, 3, Makofi. Now, have you heard what she said? Now, what were you appreciating? You stand up. Tell them the principle of conservation of energy. Energy can neither be created nor destroyed, but can only be transformed from one form to another. If I am moving like this, I am bragging around the campus of Mbarara Army. What form of energy do I have? Talk. If Israel is walking from one point, what form of the energy do I? It's called? When I stop, does it die away? What happens to it? It becomes what? Potential. So I am sorry to say, but the principle says that not even God can create energy. No, it states, we are not debating, I'm quoting the principle. You don't take me to your pastors and tell them the other man is Not even God. Are you debating or you are arguing? She has said that this thing, it means it is a negative. Nobody can. So neither God nor man can create the energy, nor can the two destroy it. We are all playing around, changing it from one form to another. If I have electrical and I want light, I get a bulb. It converts it from electrical to light. If I want to blast music, if I want to blast what? Music, I have electrical. I can put on a speaker and it blasts the music. These days, I'm in love with a song that says, "Son, my life is over and yours has just begun." So you people, our lives are actually getting to, and yours are just starting. That is the reality. I am clocking 40s. Many of you are still 18, 19. Those who are too old, they are 21. So me, I am actually getting, today we had a meeting with the head teacher. And the first point he made in his kind of the talk, he told us that the moment you earn your first salary in the army, plan for your retirement. Now, I have earned about 2 years of the salary. So why don't I plan for the retirement? You mean I will teach, and this man comes, he also teaches, and we sit in the same room? Bano nga bakava ku university babeera n'olugezigezi, and the school will give them appointments. He will be the boss. You imagine he will be the boss, and I'm still a classroom teacher. He gets his phone. Hey, Israel, where are you? Senior one here is making noise. Can you please come and teach them? So once you wake up one morning and one of the students you taught is also a member of staff, either resign or retire or ask for a transfer. Yeah, I'm telling you. That's what they informed us, that the moment you get the first pay, plan for the retirement. So I am saying that if you want to convert from electrical to sound, you get a speaker. But it will not mean that you have created the sound. Are we together? And so on and so forth. So in this case, we are going to look at the energy stored in a capacitor. And we have generated it from the fact that the moment there is any movement of one point, the object from a point to another, there must be a energy. So how does it exist in a capacitor? You write and say, suppose the PD between the plates at some instant. Suppose the PD between the plates at some instant. Suppose the PD between the plates at some instant. Suppose the PD between the plates at some instant was V. Suppose the PD between the plates at some instant was V. Full stop. When a small charge of how do you read this? Sigma. Then this delta. So when a small charge of a positive small charge Q, or sigma Q, when a small charge of that is transferred from a negative plate to a positive plate, when a small charge that is transferred from the negative plate to a positive plate, a comma, the PD increases by a small change in V. The PD increases by a small change V, or a small PDV. Actually, this is read as a small charge or a small PD. In mathematics, you have what you call small change or change, which is a samosa, like that. All right? Okay. Full stop. When a small charge, a small positive charge is transferred from the negative plate to the positive plate, comma, the PD increases by that. The PD increases by by that. Full stop. New line. Work done to transfer charge. Work done to transfer charge. Work done to transfer charge. Now, if the plates already had a PD and you added a small charge from one plate to another, meaning you will have done a small what? A small work. Which small work? Equals the V that was there plus the small v that you've added there times the small q that was transferred from one point to another. Because when we're looking at the Coulomb's law and the electric fields, we say that work done in transferring a coulomb of charge from one point to another equals the product of that charge times the PD. Are we together? So this one, we are saying that if you have done it in small capacities, you transferred a small charge from one plate to another and it brought about a small increment in the PD, then you will have done a small work. Are we together? Are we together? Are we together? So if you want to have the total work that you have done, you are going to add all the small works that you have and get a big total work done. So if you expand this, the mathematicians, my daughter there, what is your name? Please, I'm a muzei. I need the name that is. You who? You? Irene. Irene, when you expand this, what do you get? Stand up and you inform us. This is a distributive law of maths, right? That whatever is outside the bracket is going to affect everything inside. Eh? So we get a small work done as V times a small q plus a small v, please, you're talking to me, times a small what? A small q. Are we together? Now, in our assumptions, we assume that if you get a small figure and you multiply it by a small figure, what do you get? You get? Your mathematics is magwamped. A small, and check with your computers. Get a very small figure, say 0.000001. Multiply it by 0.01. What do you get? Let us try to be fast, please. We have a lot to do. If you get a smaller number, multiply it by a smaller one, you get a much smaller one, isn't it? What you get is smaller than any of the two, which we say that it tends to what? To zero. So we are going to eliminate this term from that assumption. But this term will tend to zero because a smaller figure multiplied by a smaller one, you get a much smaller what? Now, what about a small one plus a small one? What do you get? You get a big one. So that one is going to work here. When we get a small work plus a small work plus a small work, we get the total work done. So in this case, we shall have the small work equaling to V times a small charge what? 2. Now, meaning that if you want to get a bigger work, you are going to add this one from the zero work you had to the work when your Q was a significant value of Q. Have you studied integration in maths? No. So you will capture this today. When you study integration, you come back and check for the mathematical facts. Because for me, I don't teach mathematics. Teaching you the integration of a polynomial function, exponential function, my senior Oroma. Is he teaching you? He will teach you through that maths. So, but what about Were? He will also teach you maths. Doesn't he teach you maths? So, but V equals Q over C. So, the small work done is going to be Q over C dq, all times the small change in Q. Therefore, the total work done to charge the capacitor, the total work done to charge the capacitor to a charge Q, Q is going to be W, because I will add this plus this plus this. If you are adding very many small changes in mathematics, you're literally integrating, right? So we shall integrate it from 0 to Q of Q over C dq. Huh? That's what I said, that when Oroma comes and teaches you the integration, then you refer to this. So you quote this the way it is, and then after understanding the mathematics principle of integration, you will come and refer. But for us, at the moment, we shall only be using the final expression. Are we together? Yeah, so don't get, don't be pissed, mad at me. The man is giving us the mathematics. No, I am borrowing the mathematics, because all of you here are doing at least physics and maths. And nobody is doing physics without maths. If you are here, you are in a wrong place. So if you integrate this, convince, after you have looked at the mathematics, you will convince yourselves that you will get W as the work done as a half Q squared over C, Q squared over C, and then substituting for Q, but Q equals CV, so we shall have our work done as a half CV squared. So I'm sure the confusion is here, isn't it? But I have said, don't worry. Don't worry, they will teach you integration. After they have taught it to you, it will make sense. But for now, I have to take you through the first principles. You must study the functions first. Know when we integrate a function with respect to another. It's a long story. So I want to quote the mathematics today. When you study integration as a topic, you will come back and this will make sense. Please, you allow me do that. Otherwise, if I again go into teaching this, it will cost us another full term. So you quote it the way it is. We are going to be using this severally, where if you know C and V, you can get the work. But even if you know Q and C, you can get the work done by a capacitor, or the energy stored in a capacitor. If you know V and C, still you can, if you know V and Q, still you can substitute and find the work done, or the energy stored in a capacitor. Capacitor networks. You have it, you want to write? Capacitor networks. What's up? Why aren't you writing? Where is your book? You are lying. Capacitor networks. That sign is an elongated S. Make it a little longer in that you can write the lower limit and the upper limit. All those ones are mathematical terms that a colleague or Roman Matthew will introduce to you when time comes. So capacitor networks. Now in this part, we are going to look at how we can arrange the capacitors more than one, depending on the capacitance that we want out of them. Ladies and gentlemen, if you have a number of capacitors and you want to get, after arranging them, and you want to get a smaller capacitance, what would be the best arrangement? Or if you have a number of the capacitors and you want to arrange them, but you get a bigger capacitance, what will be the arrangement? So you can write and say there exists two types of capacitor networks. There exists two types of capacitor networks. There exists two types of capacitor networks, i.e. there exists two types of capacitor networks, i.e. parallel network. Parallel network. You know parallel lines, right? In mathematics. These are lines that do not what? That do not meet. I hear even some people when they are speaking in English, they say, me and that person, we are parallel. Is it meaningful? What does that mean? Like, if somebody says like that, me and this guy here, we are parallel. What does that mean? We don't have anything that can make us meet. Ideally, I don't need that person, isn't it? In mathematics, there are three types of lines or four. 1, 5, 5. You mentioned 6, I will make you stand up and you outline them. I know 4 at least. 1, parallel, that they do not what? 2, perpendicular. They meet at what? At right angles or at the 3. If all lines are straight, do we have a circular line? The parallel, perpendicular, those ones you know. Then there are those ones that are skew. You know skew? Skew lines. These ones, they are not parallel, but they don't meet. As I've said, they are skew. You can have them like this. They don't meet. I am giving you information. You want to doubt my mathematics? Then the third ones are called what? I mean the fourth ones. You go and ask the maths teacher. So parallel capacitors are those ones that they share the same PD. The PD is connected across the ends of the combination of the 3. This is what we mean. If you have a capacitor, and a third one, you connect them first, then you give them a source of EMF or PD. Maybe this is capacitor C1, capacitor C2, capacitor C3. So for parallel plates capacitors in parallel arrangement, it means that they share the same PD what? PDV. The PD across the capacitor of capacitance C1 is the same as the PD across the capacitor. Is the same as the PD across the capacitor of capacitance C2, the same as the PD across the capacitor of the capacitance C3. Now, if the PD is the same, so what do they have different? What do they have different? What do they have different? The charge. So the charge on a capacitor C1, when charge is produced from the source, when charge is produced from the source, it flows, and the moment it meets a junction, the moment it meets a junction, part of it will take part of the branch, another one will also look for the branch, and also the other one looks for the branch. If the branches are 5, the charge will also split itself into 5 branches. So it means the capacitor of the capacitance C1, basing on how big it is, because Q equals C what? CV, which means that the capacitor of a capacitance C1, if C1 is big, holding V a constant, it will mean that Q will be directly proportional to C. So it means that if this has a bigger capacitance, it will hold a bigger charge. Are we together? But if it has a smaller capacitance, it will take a smaller charge. So in this case, to get the effective capacitance, in this case, to get the effective capacitance, we shall conserve what? The charge. We shall conserve the charge that was produced from the source is not going to be destroyed. It's going to be conserved, which means that the one you produce, Q, equals the one that goes through a capacitor C1 as Q1. Are we together? Plus the one that goes through a capacitor C2 as Q what? Q2. Plus the one that goes through a capacitor C3 as what? Q3. Wake up, Iran. If you feel like sleeping, you go take some small water and come back. Are we together? So in this case, for parallel network, charge is conserved. The charge that you produce from the source equals the charge that is distributed through all the 3 capacitors. But the charge on a capacitor Q1 equals C1 V. Do you know why we are taking V, not V1? Because the 3 have the same PD. Then the charge Q2 is C2 V and Q3 is C3 V. Let us try to substitute this back here. So we shall have Q equals C1 V plus C2 V plus C3 V. V happens to be a common factor. Factor it out and have Q equals C1 plus C2 plus C3 times what? V. Bring it this way. When you bring it this way, divide both sides by, you will have Q over V equals C1 plus C2 plus C what? So what is Q over V by definition? C. Therefore, the effective capacitance of the arrangement this will be the sum of all the capacitors. So it will be C1 plus C2 plus C what? C3. Now this is the effective capacitance of capacitors arranged in a parallel network. Now we are saying that if you have n capacitors, if you have n capacitors, you don't only have 3, you have about 1 million capacitors. So for n capacitors, the effective is going to be C1 plus C2 plus C3 plus other many, C4 plus C5 plus 6. So we plus other many plus C what? Cn. So the effective capacitance is the sum of Ci, I running from 1 to n. Pardon? Eh? Pardon? What are you trying to say? This one here, summation. You don't remember the summation? Yeah? Auntie, I have started by showing you here that I runs from 1 up to n. So if you have 1 capacitor, the capacitance is going to be C1. If you have 2, you'll have C1 plus C2. You remember how you used to find the average or the mean, X bar? It is summation of Fx over summation F. You didn't do this? It's what ideally I'm doing here. Hey. It's what I'm doing here. Eh? From where, my brother? From here. So this is the problem. Okay. Is it still there? Problem solved. Yeah? So with experience, you will come to it. You will do, in mathematics, you do probability. Eh? You will study, you will meet this in maths. So let's leave it in physics. You find it in maths. The continuous and discrete probability, the functions. So those who want it, you can take note. But those who don't want it, you can leave it there. You see, there is a man on TikTok who says he was sick. And the doctor told him that you are going to live for only 1 year. So this man was a gangster. He had a gun. Pulled out his gun and shot the doctor. The doctor died. Now they took this man to the courts of law. And the judge gave him 18 years in jail. So the man was like, problem solved. The doctor gave me 1 year and I shot him. The judge gave me 18 what? Years to live in jail. And I want to believe that man is still there. Series, network, or arrangement? Hurry up, we have less than 30 minutes. So now we are going to answer the question of if you have a number of the capacitors and you want to arrange all of them and you need to get a smaller than the capacitance, what arrangement would you prefer? Let's look at the series and see now. For series, the capacitors are arranged one end of the other one to the end of the other one. So if this is C1, this is C2, and this is C what? C3. Now, in this case, can we look here? Irene, In this case, when charge, because charge is the one that flows, PD is across the end. So here we saw that when it flows and it meets, you people come from homes that have good plumb work, where a tank is put at a given height from the floor, then one pipe comes from the tank. Is it the case? Then you find that at your home, this water, part of it goes to the kitchen, right? Part of it goes to the toilet, part of it goes to the bathroom, part of it goes to, some people now put a tub for washing the hands at the entrance, isn't it? So all those are separated from a point and they get what we call a parallel arrangement, such that when it comes from the source and it meets all the pipes that are at the junction here, will take. I don't know how right it is, but they used to tell us that those days, when we used to still have roundabouts in the country, you know, the reason, this is an explanation from lay people. They say the reason as to why all other vehicles are supposed to stop when the fountain of honor is moving is that when he meets a roundabout like this, and they are coming from this way, if the convoy has 1, 2, 3, 4, 5, and 6, when one takes this route, where will 2 go? 2 will take this one here. 3 goes this way, 4 comes this way, 5 that way, 6 this way. But when they come to this end, they again arrange themselves the way they were here. So that is one form of parallel arrangement. That when you meet a junction, the thing that flows will actually go through all the branches of the junction. That is why in this case here, charge, it splits, but PD does not. It's the same, because PD is always across the ends. So the PD across these ends is the same as the PD across this and the PD across that. Now here, when charge tries to flow, it comes to a capacitor of capacitance C1. There is no junction. So the charge that is attained here will also be the same charge attained here, or flows through this and that, then it comes back. But these 3 have different ends. This one will have its end, and the PD across these ends will be V1. So the amount of energy that it will take will depend on its capacitance. Because from V equals, okay, from C equals Q over V, V is inversely proportional to C. So the bigger the C, the smaller the V. So if this one has a bigger capacitance, it will grab a small PD. Then the same applies to this V2, and the same applies to this V what? V3. Because there is no branch where the charge is going to take, the charge on this is the same as the charge on that, and the same as the charge on that capacitor. So in this case, what is conserved? Previously, we conserved charge because it is the one that keeps on splitting. So in this case, what are we going to conserve? Yeah? So conserving the PD, the PD you produce, or the PD of the source, will equal to the PD of the PD across the ends of a capacitor C1 plus the PD across the ends of a capacitor of capacitance C2 plus the PD across the ends of a capacitor of capacitance C3. Are we together? Now we go into algebraic gymnastics. So we shall have, but what is V1 equal to? Q over, is it Q over C1? V2 equals Q over, and V3 equals Q over So substituting back here, we shall have V equals Q over C1 plus Q over C2 plus Q over C3. Meaning Q is a common factor. Factorize it out. So you'll have V equals Q into 1 over C1 plus 1 over C2 plus 1 over C3. Divide both sides by Q and have V over Q is what? Are you sure? It is the inverse of C. The reciprocal. Huh? The reciprocal. It's called the reciprocal. You see, in this life, mathematics is too much. Life can make things reverse, reciprocal. Today you might be in the driving seat. Then tomorrow you might be being driven. Like Dube says that be good to the people on your way up the ladder, because you will need the same people on your way down the same ladder. Isn't it, Irene? Don't you think you will need them? You need these people who clap for you as you're moving up. You need them. But then when you're coming down, their hands will be there for you to step on. Okay, so if this is the reciprocal, I wanted to spell the word reciprocal for that guy. It's not reciprocal. It is reciprocal. But in primary, they just taught you to pass exams. So if you become a teacher and you meet an audience that has people like me, we shall keep on challenging you here and there. So this is going to be the reciprocal of C as 1 out of C equals 1 out of C1 plus 1 out of C2 plus 1 out of C what? C3. Now again, I will bring in the other mathematics of summations. Now, if you have n capacitors, now we are going to check whether if we have a number of capacitors and we want all of them to be in the circuit, but we want a small capacitance, which of the two do we use? Let's try. All of you are going to check for this. Check for when C1 is maybe 1 Faraday and C2 is what? Is also 1 Faraday. What will be the effective for parallel arrangement and what will be the effective for series arrangement? Check. Check aside, substituting into the expressions. Check, human, check aside this way. Don't be bored. Mathematics and physics are not boring subjects. Every time you have a paper and noting something. For parallel. Wasn't it? Yeah, so substitute for C1 and C2 and see what you get. Then for series, now if you want to use, if you have a number, what do you get for the capacitance effective for parallel? You get 2. Then here, you get, are you sure? You have a calculator. You get a half 1. What do you get, human? You haven't tested. And got? I think you are getting. Can we check? For parallel, it is C1 plus C2, right? Which is 1 plus, so you get 2 for parallel. Then for series, you will get 1 out of C equals 1 out of C1 plus 1 out of C. So 1 out of C will be 1 over 1 plus 1 out of 1. Which is also 2. You guys, you stop that habit of. So 1 out of C is 2. Okay? But it's the reciprocal. So this is 2 over 1. So if I reciprocate this, it becomes C, then this one has a half. Now, where are those people getting 1 from? From what? Confusion. Confusion is in this room. Yes. Hey. Now, this man is saying for a special case. So continue from here. And say for a special case of 2 capacitors. For a special case. For a special case of 2 capacitors. For a special case of 2 capacitors, we shall have 1 over C equals 1 over C1 plus 1 over C what? C2. Let me fix it in the small space possible. So here we shall have 1 over C equals, what is the LCM here? Somebody is saying 1. C1, C2. So the whole of this divided by this, you get C2 times 1. Plus the whole of this divide this times 1. So you'll have 1 over C1, 1 over C equals C1 plus C2 over C1, C2, which is sum over the product. But now this is 1 out of C. But we want C. You flip it. So it will be C equals, convince yourselves, C1, C2, C1 plus C2. What this man is saying, it is the product over sum. Examples. Now, they tell us that when teaching, you must teach from known to unknown, simple to complex, seen to unseen. But for these examples, I'm going to give from complex to simple. You people provoke the teachers on media that teachers teach in class 1 plus 1 equals 2 as the classroom what? Work. Now the exam says John is 2 years old. The plane is flying northwards. What is the weight of the plane and John in the southward direction? Now you find somebody sweating and there is a saucepan just down here. You people have provoked teachers like nothing. So, examples, a battery of EMF 12 volts, a battery of EMF 12 volts, a battery of EMF 12 volts is connected across a system, a battery of EMF 12 volts. A battery of EMF 12 volts is connected across a system of capacitors. A battery of EMF 12 volts is connected across a system of capacitors. Full stop. Calculate the total energy. Calculate the total energy stored in the capacitor network. Calculate the total energy stored in the capacitor network. Calculate the total energy stored in the capacitor what? Network. Now, always make sure that you track the flow of charge. The only tool or technique that will help you to know whether these are in parallel or in what? Series is to track the flow of charge from the source or from the battery. So all the numerical problems that you are going to solve, make sure that you keep tracking the flow of what? Of charge. So in this case, charge is going to flow from here towards the positive terminal. So when it comes from here, it reaches here, the capacitor, which means that by the time it reached here, it did not come across a junction, right? So it went through an opposite wholesomely. Are we together? Now, when it went through this wholesomely, it met a junction here. Are we together? When it meets a junction here, part of it is going to go through the 2 microfarad capacitor, and the other one is going to go through the 3 microfarad capacitor. Now, the moment you spot splitting of charge, that should be the confirmation that those two are in parallel. Now, again, before you solve them for, excuse me, before you again attack them to put them into one, first finish the flow of that charge. You might find that again, as it goes like that, it meets another two that are either in series or in parallel. Are we together? So when you track this one, this charge, it goes only through this. Then the one that went downwards, it also goes through this. Then they come and meet where? Here. Then when they come back, they go as, or it goes as it was produced. So then you confirm that I am going to only squeeze these two, because when I squeeze them, the charge that enters will be the charge that leaves. Are we together? So meaning that I will start by these two. These two are what type of the arrangement? Find for me the effective capacitance of capacitors in parallel. Ayebare, what happened to the book? Ayebare, aren't those excuses? You must carry all your books every day on your backpack. Now you people, you see, if carrying these books is expensive, you buy a car. Yes, you buy a car and put in your books, then you park it there. Because the only thing they don't allow here is to drive when you are a student, right? But I see some boys, I think in S5, riding a motorcycle. So if they don't want you to drive, you buy your car. Come with your father on the reporting day, you park it there and lock it. Put your books there, your drinks and what have you. So every time you want something, you go, press the nani, open your car, pick your books. Isn't it? Because now to carry the books on a backpack or in a backpack is expensive. Buy a car. In Uganda we say omugagga si muntu. Bw'ayagala ekibumba atta nte namba naga anjagala kulyamu kibumba kyokka. That is who we call a rich man. But now if you want to eat a liver, you go to the butcher and buy half a kilo. Don't count yourself among those who have the money. Tante kill the whole, then tell them that I only want the liver, then give the rest of the beef to the dogs. Then society will say, there is a man this side called Hassan Basajjabala. Do you know him? He's another rich man, I think, in Uganda. In Kampala, in Ankole, and in Uganda at large. He usually have his, I tell people here that for us in Kampala, there are people who 2 million is not enough for them a day. E Kampala waliyo abantu nga million 2 tezimala olunaku. Naye kati gwe ne bazikuwa ofana z'omwaka mulamba. Struggling with finishing 2 million. But Kampala there are those guys who even 10 million is not enough in a single day. By the time I was still a hustler, I had a brother who used to ride a motorcycle. So those 4-star hotels in Kampala, food is free of charge at night. When they prepare that food and people do not eat it, I am telling you the stories, but as you're writing, Irene, don't pay attention to the stories. So those of us who are hustlers in the city center, we could time that night time when food has been made free. We come and eat. But now the hotel people are wise. When you enter to eat, they lock the hotel and they give you plates. You wash them in the night. So you eat your food, get satisfied. On looking for the exit, you find a scan, a UPDF man, not laughing at all, tells you to go back and wash the plates. So at the end of the day, people in school are like, yeah, I want to be like Israel. I want to be like Israel, my friend. I washed plates. I washed plates after eating food for free. And this food, it was, you time it because they open the gate at midnight exactly. At midnight up to 30 past this time. You eat the food buffet, self-service, because now that one they cannot keep it for the following day. Now after you have eaten, the berry is this size, you want to move out, the man tells you, please go back and wash the plates. And the plates of those hotels, my friend, you can wash them up to the following day like at this time. So I was like, emmere eno ey'obwerere sijja gisobola. What do you have here? Huh? Are you sure? Let me sample about 4 people. What do you have? What did you use? 1 out of C1 plus 1 out of C2. Eh? 1 out of C equals 1 out of C1 plus 1 out of C2. What did you use? 1 out of C equals 1 out of C1 plus 1 out of C2. Use this. I think he has a wrong answer. If he used this. If we are squeezing this, and these two are in parallel, did you use this? You used the C equals C1 plus and got 5. Then you are right. So we squeeze this. Allow me squeeze this. I was trying to test him, but he's... Then you man there. You have this 5. So after you have got that effective, if you have the space, you redraw the circuit. And when you redraw the circuit, you will get something that looks like this. You will get something that looks like this. So this is what? 5 microfarad. Now these two are in what form of arrangement? Series. Find me the effective of 2 in series. Pardon? 2.5. So again, I can rub this. And have 2.5 microfarad. Now, ladies and gentlemen, all the other capacitors that we had, the 5, the 3, and the 2, their effective in the circuit is what? Is what? 2.5. Which means that if you have a number of capacitors and you want them to give you a small capacitance, you arrange them in series. Are we together? Are we together? So then here, can't we find the energy stored in the system? Eh? Can't we find the energy stored in the system here? Energy equals a half CV squared. So our energy is going to be a half times C, which is 2.5 exponent negative 6 times what? Times 12 squared. On Wednesday, don't dare come in here without a calculator. See, put your calculator here. When they steal one, you buy another one. That what? You are irresponsible. Me, I bought that thing before I joined the army. Up to now, I have it. This one here. You mean I've not worked ever since I bought it? It does no work. What do you have here? Yeah? Hurry up. 1 point exponent negative 4. What are the units? Yeah? Joules. The figure above shows a network of capacitors. The figure above shows a network of capacitors. The figure above shows a network of capacitors connected to a 10 volts battery. The figure above shows a network of capacitors connected to a 10 volts battery. Calculate the total energy stored in the network. 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 Now listen, you are going to do that number. And whoever will attend my class on Wednesday towards break, I must have marked that work and signed against. You know, when I mark, how many of you have I marked yet? At least I mark your book, I comment, I put a date, and I sign. So if you don't have those three, don't dare present your morphology on that day. Am I clear? But even in the working, you remember how I've solved the previous problem here? To the extent that I come up with one capacitor being connected to a battery. So every two capacitors you squeeze, either in parallel or in series, draw the circuit. Am I clear? I will be marking one, the identification that the two are in parallel or in series. Then I look at the circuit diagram. If it's not there, my friend, I will cross you with morale. I wish you the best.